Hello, gentle traveler of the night. Welcome to a place where science whispers softly, where questions linger longer than answers, and where the universe reveals itself slowly, like stars appearing one by one in the deepening dusk. Some nights, when the world finally falls quiet, a single thought can break through the silence. You look up at the stars scattered across the darkness like ancient light frozen in time, and you wonder if everything is moving, expanding, stretching farther into the void. What exactly is it expanding into? What lies beyond the edge of everything we know? It's the kind of question that feels too big to hold, too strange to answer. And yet it pulls at something deep inside. Because if the universe is growing, shouldn't there be something outside? Shouldn't there be a room? It's filling a space, it's claiming a boundary, it's crossing. Before we drift into this mystery together, I want to invite you to stay a while. If you find comfort in these quiet journeys through the cosmos, you might like to gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. You don't have to, of course, but if you do, know that it helps these whispers reach others who need them too. Now, let's drift. Tonight we are going to explore one of the most beautiful, bewildering questions humanity has ever asked. A question that doesn't just live in textbooks or observatories, but in the quiet moments when you're lying awake, staring at the ceiling, wondering about your place in all of this. The universe is expanding. That much we know. But expanding into what? The answer, as you'll see, is far stranger than any edge, any wall, any boundary you could imagine. You don't need to understand everything. Just rest and let curiosity do the listening. The question itself is ancient. Long before telescopes, before Einstein, before we even knew what a galaxy was, humans looked up and asked, does the sky go on forever? The Greek philosopher Archytas, around 400 BCE, posed it beautifully. He imagined standing at the edge of the universe, whatever that meant, and throwing a spear. If the spear flies onward, then there must be more space beyond. But if something stops it, then that something must exist in space, which means the universe extends further still. Either way, the edge keeps retreating. It's a thought experiment that refuses to resolve a puzzle that tangles the more you pull at it. Aristotle, not long after, argued the opposite. He believed the universe was finite, bounded by the sphere of stars, perfect and unchanging. Beyond that sphere, nothing. Not empty space, not darkness. True nothingness, an absence so complete it couldn't even be called a place. For Aristotle, the idea of infinity was uncomfortable, almost offensive to reason. How could something go on forever? How could there be no end? And so he drew a line, declared the cosmos finite, and for nearly 2,000 years, much of the Western world believed him. But belief and truth are not the same thing. In the late 1500s, an Italian monk named Giordano Bruno dared to think differently. Bruno wasn't a scientist in the way we'd recognize today. He was a philosopher, a mystic, a dreamer who looked at the stars and saw not a ceiling, but an invitation. He proposed that the universe was infinite, filled with countless worlds, each one orbiting its own sun. No center, no edge, no boundary where God's creation stopped and nothingness began. It was a radical, terrifying idea, and the church didn't take it well. In 1600, they burned him at the stake in Rome, not just for this belief, but for refusing to recant it. His last words reportedly were defiant. "You who sentence me are in greater fear than I who am sentenced." Bruno never saw proof of his infinite cosmos. He had no telescopes, no equations, no evidence beyond the force of his imagination. And yet, in a way, he saw further than most. He understood something essential, that the universe doesn't care about our need for edges for comfort, for things to make sense on human terms. It simply is. Centuries later, we're still wrestling with his question, not philosophically anymore, but scientifically. And what we've found is somehow more astonishing than either Aristotle's bounded sphere or Bruno's infinite expanse. Because the universe, as it turns out, might be both. Here's where it starts to get strange in the way only the cosmos can be strange. When we say the universe is expanding, we don't mean it's growing into some pre-existing space like water filling a bathtub. We mean that space itself is stretching. The fabric of reality, the very stage on which matter and energy perform, is getting bigger. Imagine a balloon with dots drawn on its surface. As you inflate the balloon, the dots move apart, not because they're traveling across the rubber, but because the rubber between them is expanding. The dots aren't moving, the surface is. Now, here's the part that breaks most people's intuition. If you're a dot on that balloon, you'd see every other dot moving away from you. And if you were on any other dot, you'd see the same thing. Every point appears to be the center of the expansion. There is no special location, no privileged perspective. The universe is expanding everywhere all at once, and it's not expanding into anything because there is no outside for it to expand into. This isn't just poetic language. This is what the mathematics of general relativity tells us. Space and time are woven together into a single fabric space-time, and that fabric can bend, stretch, and curve. When we ask, what is the universe expanding into? We're asking the wrong question. We're assuming there's a container, a stage of pre-existing void waiting to be filled. But the stage is the universe. There is nothing beyond it, not because there's a wall, but because beyond doesn't exist. It's not that we haven't found it yet. It's that the concept itself has no meaning. Think about it this way. If you walk around the surface of the Earth, you can keep going forever without ever reaching an edge. The surface is finite, measurable, but it has no boundary. You're not walking into new territory that didn't exist before. You're moving through a space that curves back on itself. The universe might work the same way, just in more dimensions than we can easily visualize. It could be finite in size, but unbounded, a closed loop in space-time that has no edge because it folds back into itself. Or it could be infinite, truly infinite, stretching forever in all directions with no end, no edge, no final star marking the border of existence. If that's the case, then the expansion isn't adding new space to an existing infinity. It's stretching an infinity that was already there, making the distances between galaxies grow larger without ever filling up or running out of room. An infinite universe doesn't expand into anything. It just becomes a bigger infinity, which sounds impossible, but mathematics allows it. Infinity isn't a number. It's a concept that can contain more or less depending on how you measure it. Both possibilities are equally unsettling. A finite, unbounded universe feels claustrophobic in its own way, a cosmic hall of mirrors where you could theoretically travel far enough to loop back to where you started. An infinite universe feels too vast, too empty a place where you could drift forever and never reach the end. Either way, there's no edge, no wall, no place where the universe stops and something else begins. And yet, we keep asking, what's beyond? It's built into us, this need to find boundaries, to map the edges, to know where we stand in relation to everything else. For most of human history, we lived in worlds with edges. Oceans had shores, forests had clearings. Even the sky, once thought to be a solid dome, was something you could imagine touching if you climbed high enough. But the universe doesn't offer that comfort. It stretches our language, our logic, our sense of scale until they break. Here's a question for you, one to carry quietly as you drift towards sleep. If the universe has no edge, no outside, no container, it's filling. Does that make it more mysterious or less? Does it feel lonelier knowing there's no wall to touch, no final horizon to reach? Or does it feel freer knowing that existence doesn't need permission, doesn't need a frame, doesn't need to make sense to us? In order to be, scientists don't talk about edges anymore. They talk about the observable universe, the bubble of space from which light has had time to reach us since the Big Bang. That bubble is vast, roughly 93 billion light years across, and it's growing as more distant light finally arrives. But it's not an edge. It's just a horizon, a limit on what we can see, not on what exists. Beyond that horizon, the universe continues. Galaxies shine in the darkness unobserved. Stars are born, burn, and die without ever sending us their light. Space stretches onward, indifferent to whether we're watching. And the expansion. It's accelerating. Galaxies aren't just drifting apart. They're drifting apart faster and faster, pulled by something we call dark energy, a force we don't understand, can't see, and can barely measure. It makes up nearly 70% of the universe, and it's tearing everything farther apart with each passing moment. One day, billions of years from now, the galaxies beyond our local group will have receded so far, moving so fast, that their light will never reach us. The universe will look smaller from Earth, not because it's shrinking, but because the expansion will have carried the distant stars beyond the horizon of what we can ever see. Future astronomers, if they exist, might look up and see only darkness, never knowing how much was lost to time. It's a kind of loneliness written into the fabric of space-time itself. The universe is expanding into nothing because there is no into. There is only the endless patient stretching of space and us small and brief trying to understand it. But maybe that's the beauty. Maybe the answer isn't a place or a boundary or a map with edges. Maybe the answer is simply this: the universe is. It doesn't need to expand into something to be real. It doesn't need our understanding to continue. It just is vast and strange and utterly indifferent, and somehow we're here awake in the middle of it, asking questions into the dark. You don't have to solve this mystery tonight. You don't have to hold the whole universe in your mind. Just let it wash over you, the strangeness of it all, the quiet wonder of a cosmos that refuses to be contained. And as you feel yourself beginning to drift, as your thoughts soften and blur at the edges, know that the questions we ask are often more beautiful than the answers. The universe expands, space stretches, time moves forward, and we, for this brief moment, get to witness it. But how did we even discover this expansion? How did we go from ancient philosophers throwing imaginary spears at the edge of the cosmos to knowing with certainty that every galaxy is racing away from us? That story begins not with a question, but with a stubborn refusal to believe what the universe was trying to tell us. Long before telescopes pierced the darkness, before equations described the curve of space-time, humans sat beneath the same stars we see tonight and asked impossible questions. Does the universe end somewhere? Is there a final star, a last breath of light, beyond which nothing exists? Or does it go on forever, infinite and uncontainable, stretching past the limits of imagination itself? These weren't just philosophical games played by scholars in marble halls. These were questions that haunted people, that kept them awake, that made them look up at the night sky with equal parts wonder and terror, because the answer, whichever it was, seemed unbearable. A universe with an edge felt small, confined like living in a cage you could never see but always feel. But a universe without end felt too vast, too empty a place where you could wander forever and never arrive anywhere that mattered. The ancient Greeks were perhaps the first to wrestle with this problem in ways that still echo today. Around 450 BCE, two philosophers named Leucippus and Democritus proposed something radical: that the universe was infinite, filled with endless worlds, each one floating in an eternal void. They believed that atoms, tiny particles too small to see, combined and separated across infinite space, creating and destroying worlds in an endless cosmic dance. There was no center, no edge, no place where creation stopped. Just infinite possibility forever. It was a beautiful idea, almost modern in its scope, but it terrified people. Because if the universe is infinite, then where do the gods live? Where is the order, the structure, the meaning we crave? An infinite universe doesn't care about us. It has no center stage for humanity to occupy, no special place where we matter more than anywhere else. And so, unsurprisingly, the idea didn't catch on. Not yet. Aristotle, who came a century later, built his entire cosmology around the opposite belief. For him, the universe was not only finite, but perfectly ordered, a series of crystalline spheres rotating around the Earth, each one carrying a planet or star in its eternal orbit. Beyond the outermost sphere, the sphere of the fixed stars, there was nothing, not empty space waiting to be filled. True nothingness, an absence so complete that it couldn't even be called a place. To ask what lay beyond the stars was to Aristotle like asking what color silence tastes like. The question itself was nonsense. And for nearly 2,000 years, Aristotle's word was law. Medieval scholars in Europe, the Islamic Golden Age, even early Renaissance thinkers, they all worked within his framework. The universe was a finite sphere bounded and knowable with Earth at its center, and God somewhere beyond the stars, holding it all together. It was comforting. It made sense. It gave humans a place in the cosmic order, but comfort and truth don't always align. In 1277, something curious happened. The Bishop of Paris, Etienne Tempier, issued a condemnation of 219 philosophical propositions, many of them drawn from Aristotle's teachings. Among them was the idea that God could not create an infinite universe. Tempier argued that limiting God's power in this way was heretical. If God is omnipotent, then surely he could create a universe without end, a cosmos that stretched forever in all directions. It wasn't a scientific argument, it was theological, but it cracked open a door that had been sealed for centuries. Suddenly, infinity was back on the table, not as philosophy, but as possibility. And then came Giordano Bruno. Bruno wasn't a scientist. He didn't perform experiments or make observations through telescopes. He was a Dominican friar turned heretic, a mystic, who looked at the stars and saw not a ceiling, but an invitation. In the late 1500s, he traveled across Europe preaching a vision of the cosmos that was for his time almost incomprehensible. He believed the universe was infinite, that the stars were distant suns, each one surrounded by its own planets, possibly even its own life. There was no center, no edge, no boundary where God's creation ended and nothingness began. Every point in the universe was equal, every star, a potential home for worlds beyond imagining. The Church did not respond kindly. Bruno was arrested by the Roman Inquisition in 1592 and held in prison for 8 years while they tried to make him recant his beliefs. He refused, not because he had proof he had none, but because he couldn't unsee what his imagination had shown him. On February 17th, 1600, they led him to the Campo de' Fiori in Rome, tied him to a stake, and burned him alive. His last words, according to witnesses, were aimed at his executioners. "Perhaps you pronounce this sentence against me with greater fear than I receive it." Bruno died centuries before we had any evidence that he was right. He never saw a telescope, never measured the distance to a star, never glimpsed the galaxies beyond our own. And yet, in his way, he saw further than almost anyone. He understood that the universe doesn't conform to our need for boundaries, for centers for things to make sense on human terms. It simply is vast and indifferent and utterly unwilling to fit inside the boxes we build for it. But here's the tragedy, and maybe the lesson: Bruno was right about infinity, but wrong about almost everything else. The universe is not filled with stars arranged randomly in an infinite void. Space itself has structure-curvature properties that Bruno couldn't have imagined. And yet his willingness to think beyond the accepted limits, to imagine a cosmos larger than the one handed down by authority, that spirit was essential. Because progress doesn't come from accepting what we're told. It comes from asking, what if? The debate over infinity didn't end with Bruno. In fact, it intensified. By the 1600s, with the telescope newly invented, astronomers like Galileo Galilei were discovering things that didn't fit into Aristotle's tidy cosmos. The moon had mountains. Jupiter had moons. The sun had spots. The heavens were not perfect and unchanging. They were messy, dynamic, real. And if the heavens could change, could move, could surprise us, then maybe they could also be infinite. René Descartes, the French philosopher and mathematician, proposed his own version of infinity. He argued that the universe was indefinite, meaning it had no discernible limits, though he hesitated to call it truly infinite, reserving that term for God alone. It was a careful distinction, a way of leaving room for the divine, while still acknowledging that the cosmos was far larger than anyone had previously dared to imagine. Descartes imagined space as a plenum filled entirely with matter in various forms, with no true void anywhere. To him, the idea of empty space was absurd. If space existed, it had to contain something, and if it contained something, then it extended as far as that something extended which might very well be forever. Isaac Newton took a different approach. In his Principia Mathematica, published in 1687, Newton described space as absolute, infinite, and unchanging, a kind of cosmic stage on which matter and energy performed their eternal motions. This wasn't just philosophy, it was the foundation of his physics. For Newton's laws of motion to work, there had to be an absolute frame of reference, a fixed background against which all movement could be measured. And that background, in his view, was infinite space itself. God, Newton believed, existed everywhere in this infinite space, perceiving all things at all times. Space was, in a sense, the sensorium of God, the medium through which the divine experienced creation. It's a beautiful, if unsettling, idea. An infinite universe, not empty, but filled with the presence of the divine, watching, sustaining, holding everything together. But it also raised uncomfortable questions. If space is infinite and God is everywhere in it, then where exactly is heaven? Where do we go when we die? Where is the boundary between the sacred and the mundane? Newton never fully answered these questions. Maybe he couldn't. By the 18th and 19th centuries, the debate had shifted from philosophy and theology into the realm of mathematics and physics. Mathematicians like Carl Friedrich Gauss and Bernhard Riemann began exploring the geometry of space itself, asking whether the universe might curve in ways we couldn't perceive, like the surface of a sphere curving in 3 dimensions, even though it appears flat to someone walking on it. This opened up a possibility that neither Aristotle nor Bruno had considered, that the universe could be finite in size, but still have no edge, no boundary. A closed curved space that loops back on itself, unbounded but not infinite. It was a strange, counterintuitive idea, and it wouldn't gain real traction until the 20th century, when Einstein's theory of general relativity made it mathematically rigorous. But the seed was planted. The universe didn't have to be either a bounded sphere or an infinite void. It could be something else entirely, something our everyday experience couldn't prepare us for. And yet, even as science advanced, the human need for answers remained. We wanted to know, does the universe end? And if it does, what's beyond the ending? If it doesn't, how do we make sense of infinity? These questions weren't just academic. They touched something deep, something almost primal, because to ask about the universe is to ask about ourselves, about whether we're central or peripheral, significant or incidental, home or adrift. Here's a question worth sitting with, one that the ancients asked and we still ask today. Would you rather live in a universe with edges or a universe without them? A cosmos you could, in theory, map completely, or one that stretches beyond all comprehension? Neither answer is comforting. Both are true in their own way. And maybe that's the point. Maybe the universe is teaching us that comfort isn't the goal. Understanding is. The ancient Greeks gave us the language of infinity. Bruno gave us the courage to think beyond boundaries. Newton gave us the mathematics to describe it. But none of them could answer the question we started with. If the universe is expanding, what is it expanding into? Because to answer that, we needed to let go of something fundamental. We needed to stop thinking of space as a stage, a container, a pre-existing void. We needed to understand that space itself is part of the universe, not separate from it. And that required a mind willing to overturn everything we thought we knew. That mind belonged to a man who loved thought experiments, who imagined riding beams of light and falling through space, who saw the universe not as a collection of objects, but as a single interconnected fabric. And when he finally put his ideas into equations, the universe revealed something no one, not even him, wanted to believe. There are moments in history when brilliance stumbles, when even the greatest minds look at the universe and see not what is, but what they want to be true. In 1917, Albert Einstein sat alone with equations that should have changed everything, equations that described a universe in motion, breathing, expanding, or contracting with each passing moment. And he made a choice that would haunt him for the rest of his life. He forced the universe to stand still. It wasn't ignorance. It wasn't carelessness. Einstein saw what his equations were telling him, and he simply couldn't believe it. Because everything he knew, everything humanity had assumed for thousands of years, whispered the same truth: the universe is eternal, unchanging, a vast cosmic clock that has always been ticking and always will be. Stars are born, stars die, but the universe itself, the universe just is. It doesn't grow, it doesn't shrink, it endures. So, he added a term to his equations, a single symbol that would hold everything in place. He called it the cosmological constant, represented by the Greek letter lambda, a mathematical trick, a fudge factor, a way to balance the pull of gravity with an invisible repulsive force that kept the universe from collapsing in on itself, or flying apart into the void. It worked perfectly, on paper at least. The universe stayed still, stable, eternal. Problem solved. Except, the universe wasn't listening. Einstein's field equations, published in 1915 as the foundation of general relativity, were more than just mathematics. They were a new way of seeing reality itself. Space and time were not separate static backdrops against which events unfolded. They were woven together into a single fabric space-time, and that fabric could bend, stretch, ripple, and curve in response to mass and energy. Matter told space-time how to curve. Space-time told matter how to move. It was elegant, profound, revolutionary. And it predicted something Einstein didn't want to accept: that the universe itself was dynamic, either expanding or contracting under its own gravity. In 1917, the evidence for a static universe seemed overwhelming. Astronomers believed the Milky Way was the entire cosmos, that the faint nebulous clouds scattered across the sky were merely gas and dust within our own galaxy. No one had measured the vast distances to other galaxies yet. No one had seen the universe in motion. And so, when Einstein's equations suggested motion, he assumed the equations were incomplete, not the observations. The cosmological constant was his way out. By adding this term, he created a repulsive force that perfectly counterbalanced gravity's pull, allowing the universe to remain in a delicate equilibrium. It wasn't that he wanted to break his own theory. He wanted to save it to make it compatible with what everyone, including him, believed to be true. But here's the beautiful, tragic irony: Einstein's original equations, before he added the constant, were right all along. The universe is not static, it's expanding. And by trying to fix what wasn't broken, he missed the chance to predict one of the greatest discoveries in the history of science. The first crack in the static universe appeared in 1922, when a Russian mathematician named Alexander Friedmann took Einstein's field equations and solved them without the cosmological constant. Friedmann wasn't trying to disprove Einstein. He was simply exploring the mathematics, following the logic wherever it led. And what he found were solutions that described universes in motion, expanding universes, contracting, universes that changed over time. He published his findings and sent them to Einstein, hoping for validation. Einstein dismissed them. He wrote a brief, somewhat curt response, claiming Friedmann had made an error in his calculations. Later, when it became clear that Friedmann's math was sound, Einstein published a retraction, but the damage was done. Friedmann's work was largely ignored, buried in obscure journals, forgotten by most of the scientific community. Friedmann himself died just 2 years later, in 1925, never knowing that his equations would one day reshape our understanding of the cosmos. Around the same time, a Belgian priest and physicist named Georges Lemaitre independently arrived at similar conclusions. Lemaitre wasn't just a scientist. He was a Jesuit, a man of faith, who saw no contradiction between the divine and the dynamic. In 1927, he published a paper proposing that the universe began in what he called a primeval atom, a singular point from which all of space and time expanded outward. It was an early rough sketch of what we now call the Big Bang, though the term wouldn't be coined for decades. Lemaitre sent his paper to Einstein. They even met in person at a conference in 1927 where Lemaitre tried to explain his ideas. Einstein listened politely, then reportedly told him, "Your calculations are correct, but your physical insight is abominable." It wasn't a rejection of the math. It was a rejection of the implications. The idea that the universe had a beginning, that it was expanding, that it wasn't eternal, felt wrong to Einstein. Not scientifically wrong, but philosophically, almost emotionally wrong. And so, the cosmological constant remained a patch on a theory that didn't need patching a solution to a problem that didn't exist. Think about this for a moment. Einstein, one of the greatest scientific minds in history, the man who reimagined space and time, couldn't let go of a belief. Not because the evidence supported it, but because it felt right. Because the alternative, a universe in motion, felt too strange, too unsettling, too much like the cosmos was alive in a way that defied centuries of assumption. It's a reminder that even genius is human, subject to bias, to preference to the quiet tyranny of what we want to be true. But the universe doesn't care what we want. By the late 1920s, the evidence was mounting. Astronomers like Vesto Slipher had been measuring the light from distant nebulae and noticing something odd. The spectral lines, the fingerprints of specific elements in the light, were shifted toward the red end of the spectrum, red shifted, which suggested these objects were moving away from us. Not just a few of them, almost all of them. The farther away they were, the faster they seemed to be receding. It was a pattern, a cosmic trend that didn't make sense in a static universe. And then Edwin Hubble entered the story, and everything changed. But we'll come to Hubble in a moment. First, let's sit with Einstein's mistake because it teaches us something essential about how science actually works. Einstein later called the cosmological constant the biggest blunder of his life. It's a famous quote repeated in textbooks and documentaries, often used to show that even great minds make mistakes. But here's the twist, the part that's almost funny in its cosmic irony. The cosmological constant wasn't a blunder at all. Decades later, in the 1990s, astronomers discovered that the universe isn't just expanding. It's accelerating, driven by a mysterious force that acts almost exactly like Einstein's cosmological constant. We call it dark energy now, and it makes up roughly 68% of the universe. Einstein's mistake turned out to be one of the most prescient ideas in physics, just applied to the wrong problem at the wrong time. So, was it a blunder, or was it a glimpse of something deeper, something Einstein couldn't have known he was seeing? Maybe both. Maybe the lesson isn't that he was wrong, but that the universe is patient. It reveals itself slowly in pieces, often through the mistakes we make while trying to understand it. The cosmological constant also reveals something about the nature of belief versus evidence. Einstein believed in a static universe not because he had proof, but because it aligned with his philosophical intuition. He once said that he wanted to know God's thoughts, that the rest were just details. For him, a static, eternal universe felt more divine, more complete, more in line with the order and symmetry he believed should govern reality. A universe with a beginning, a universe in flux, felt messy, incomplete, almost arbitrary. But the universe isn't obligated to match our sense of beauty. It isn't required to make us comfortable, and sometimes the truest things are the ones that feel most alien. Here's a question for you, something to turn over quietly in your mind. Have you ever believed something so deeply that you ignored the evidence against it? Not out of stubbornness, but because the alternative was too uncomfortable, too strange, too far from the world. You thought you understood, Einstein did. And in doing so, he missed the chance to predict the expanding universe. But he also gave us a lesson in humility, a reminder that certainty, even when backed by genius, can be a trap. By 1929, the static universe was crumbling. Observations were piling up data that couldn't be explained away, patterns that pointed undeniably toward motion. The cosmos was not still. It was restless, dynamic, growing. And the person who would finally force the world to accept this wasn't a theorist lost in equations. He was an observer, a man who pointed his telescope at the sky and let the light itself tell the story. Einstein, when he finally saw the evidence, accepted it. Reluctantly, perhaps, but he accepted it. He removed the cosmological constant from his equations, admitted that the universe was not static, and moved on. But he never stopped wondering. In his later years, he continued to wrestle with the implications of an expanding cosmos, searching for a unified theory that could reconcile gravity, electromagnetism, and the strange, unsettling fact that space itself was in motion. He never found it. But his struggle, his willingness to be wrong, to change his mind, when the evidence demanded it, that's the real legacy. Not the equations, though, they're beautiful. Not the constant, though. It returned in a form he never imagined. The legacy is this: the universe is under no obligation to make sense to us. Our job is not to force it into our frameworks, but to listen, to observe, to let go of what we thought we knew when something truer comes along. And something truer was coming. It arrived in the form of galaxies fleeing into the dark light, stretched thin by distance, and a single undeniable conclusion: the universe is not standing still. It never was. Which brings us to the man who saw it first, who measured the recession, who turned suspicion into certainty. A man with a telescope on a California mountaintop, staring into the void, watching the cosmos come alive. On a cold October night in 1923, high atop Mount Wilson in California, a man named Edwin Hubble sat alone in the darkness with the most powerful telescope on Earth. He was hunting for something specific, a type of star that pulsed with predictable rhythm, a cosmic lighthouse whose brightness could reveal distances across the void. And when he found one flickering faintly in a spiral nebula called Andromeda, everything humanity thought it knew about the size of the universe shattered in an instant. That single star, a Cepheid variable, told Hubble that Andromeda wasn't a cloud of gas within our galaxy. It was a galaxy itself, nearly 1,000,000 light-years away, so distant that its light had been traveling through space for longer than humans had walked upright on Earth. The Milky Way wasn't the universe. It was just one island in an ocean of galaxies, and that ocean stretched farther than anyone had dared imagine. But Hubble didn't stop there, because distance was only the beginning. What he discovered next didn't just expand the universe, it set it in motion. By 1929, Hubble had measured the distances to dozens of galaxies, each one a faint smudge of light resolved into billions of stars. And when he compared those distances to the velocities measured by earlier astronomers, a pattern emerged clear and undeniable. The farther away a galaxy was, the faster it appeared to be moving away from us. Not randomly, not chaotically. There was a relationship, a mathematical law connecting distance and velocity, later named Hubble's law. For every million parsecs of distance, roughly 3 million light-years, a galaxy's recession velocity increased by about 500 kilometers per second. It was as if the entire universe was fleeing from us, every galaxy racing into the darkness, the distant ones sprinting faster than the nearby ones, all of them caught in some vast invisible current pulling them apart. And if you trace their paths backward in time, if you reverse the motion and let the galaxies fall back toward each other, they all converged at a single point, a moment when everything, all the matter, all the energy, all the space itself, was compressed into something unimaginably small and dense, a beginning, not just of matter, but of time itself. Hubble's discovery rested on something called redshift, a phenomenon that had puzzled astronomers for decades. When you look at the light from a distant galaxy, you can break it apart into a spectrum, a rainbow of colors crossed by dark lines where specific elements have absorbed light. These lines are like fingerprints, unique to each element, always appearing at the same wavelengths. Except they don't. In distant galaxies, those lines are shifted toward the red end of the spectrum, stretched to longer wavelengths as if the light itself has been pulled thin during its journey across space. The explanation lies in the Doppler effect, the same phenomenon that changes the pitch of a siren as an ambulance races past you. When a light source moves away, its waves stretch, shifting toward red. When it moves closer, they compress, shifting toward blue. Astronomers had known this for years. What they hadn't expected was that almost every galaxy beyond our local group showed redshift. Almost everything was moving away. At first, it seemed like we must be at the center of some cosmic explosion, the one point from which everything else was fleeing. But that interpretation misses the beauty and the strangeness of what's really happening. The galaxies aren't moving through space. Space itself is expanding, carrying the galaxies along with it, like raisins in a rising loaf of bread. As the dough expands, every raisin moves away from every other raisin, not because the raisins are traveling, but because the dough between them is growing. If you were standing on any raisin, any galaxy, you would see the same thing Hubble saw. Every other galaxy receding, the farthest ones moving fastest, the pattern repeating no matter where you stood. There is no center to the expansion. Every point in the universe is equally valid, equally central. The universe is expanding everywhere all at once, and it's not expanding into anything because there is no outside. The expansion is intrinsic to space itself. Think about what this means for a moment. If the universe is expanding, then it was smaller in the past. Keep going backward and it gets smaller, still denser, hotter, until you reach a point where the very concept of space and time breaks down. This isn't speculation. This is what the observations demand. Hubble didn't set out to prove the universe had a beginning. He just measured distances and velocities, followed the data where it led, and found himself staring at the birth of everything. But here's where it gets even stranger. Hubble's law doesn't just tell us the universe is expanding, it tells us how fast. The rate of expansion is encoded in what we now call the Hubble constant, a number that describes how quickly space stretches. In Hubble's time, the value was wildly uncertain, off by a factor of 7 due to errors in measuring distances. Today we've refined it significantly, though there's still debate about the precise value. Current estimates put it at roughly 70 kilometers per second per megaparsec, meaning that for every 3.26 million light-years of distance, the recession velocity increases by 70 kilometers per second. That might sound slow, and on human scales it is, but scale it up across billions of light-years, and it becomes breathtaking. Galaxies at the edge of the observable universe are receding from us at speeds approaching the speed of light, not because they're moving through space that fast, but because the space between us and them is expanding so rapidly that light itself struggles to cross the growing gap. And here's the part that breaks most people's intuition: this doesn't violate relativity. Nothing is traveling faster than light through space, but space itself has no speed limit. It can expand as fast as it wants, carrying galaxies along for the ride, and there's nothing in the laws of physics to stop it. Hubble's discovery faced resistance, of course. Many astronomers, including some of the most respected names in the field, struggled to accept it. Not because the data was flawed, but because it upended centuries of belief. A static, eternal universe made philosophical sense. It aligned with the idea of a cosmos that had always existed and always would. But a universe with a beginning. A universe that was once unimaginably small, hot, dense, and is now vast, cool, and still growing. That felt too much like a creation event, too close to theology, too far from the cold, mechanical clockwork that science was supposed to describe. But the evidence kept piling up. Other astronomers confirmed Hubble's findings. The redshift was real, the expansion was real. And slowly, reluctantly, the scientific community began to accept that the universe was not the unchanging stage they had imagined. It was a story, a narrative unfolding in time, and we were living in one chapter of a much longer tale. One common misconception, one that still trips people up today, is thinking that the expansion means we're at the center of the universe. After all, if every galaxy is moving away from us, doesn't that make us special? The answer is no. And the raisin bread analogy helps explain why. From any raisin's perspective, every other raisin is moving away. There's no privileged position, no central point. The expansion is uniform, or at least approximately so, on the largest scales. We see galaxies fleeing from us because space is stretching everywhere, not because we're sitting at some cosmic ground zero. Another misconception is that the expansion applies to everything. It doesn't. Gravity holds things together on smaller scales. The solar system isn't expanding. The Milky Way isn't expanding. Even our local group of galaxies bound together by mutual gravitational attraction isn't expanding. The expansion only dominates on the largest scales where gravity's pull is too weak to resist the stretching of space. Clusters of galaxies remain intact, but the space between those clusters grows, pushing them farther apart over billions of years. Hubble himself never fully embraced the implications of his work. He was an observer, not a theorist, and he remained cautious about interpreting the redshift as evidence of expansion. In his later writings, he entertained alternative explanations, wondering if perhaps the redshift was caused by some unknown property of space that tired out light over vast distances. The idea called tired light was eventually ruled out by other observations, but Hubble's hesitation reveals something human. Even the discoverer of the expanding universe wasn't entirely comfortable with what he'd found. But the universe doesn't wait for us to be comfortable. It expands whether we understand it or not, whether we accept it or not. And as more data came in, the expansion became undeniable. Not just a quirk of a few galaxies, but a fundamental property of the cosmos itself. In 1931, Einstein traveled to Mount Wilson to meet Hubble and see the evidence for himself. He peered through the telescope, studied the data, and reportedly told Hubble, "This is the most beautiful and satisfactory explanation of creation to which I have ever listened." He abandoned the cosmological constant, admitted that the static universe was a mistake, and embraced the expanding cosmos. It was a moment of intellectual honesty, a willingness to let go of a cherished belief when the evidence demanded it. But here's the irony, the twist that makes this story almost poetic. Decades later, astronomers would discover that the expansion isn't just happening, it's accelerating. And the force driving that acceleration looks suspiciously like Einstein's cosmological constant, the very thing he called his greatest blunder. The universe, it seems, has a sense of humor. Hubble's work also gave us something precious, a way to measure the age of the universe. If galaxies are moving apart at a known rate, you can trace their motion backward to estimate when they were all in the same place. The current best estimate, based on observations of the cosmic microwave background and the distribution of galaxies, puts the age of the universe at roughly 13. 8 billion years. Not infinite, not eternal. Finite, measurable, a universe with a birthday. That's a staggering thought. Everything you see, every star, every galaxy, every atom in your body emerged from a single searing moment, 13.8 billion years ago. And it's still unfolding, still expanding, still writing the next line of its story. Have you ever wondered what it would feel like to stand at the birth of something vast, to watch the first light spread across the darkness, to see space itself unfurl like a flower, opening in slow motion? We can't witness the Big Bang directly, but we can trace its echoes, measure its remnants, piece together the story from the clues left behind. And every redshifted galaxy, every stretched photon is a message from the past, telling us how it all began. Hubble's revelation didn't just change astronomy. It changed our sense of time, of scale, of what it means to exist in a cosmos that had a beginning and will someday have an ending. It made the universe feel less like a museum and more like a living thing, growing, evolving, moving through time in ways we're only beginning to understand. But knowing that the universe is expanding still leaves us with the original question, the one that haunted philosophers and now haunts us. If space is stretching, what is it stretching into? Hubble gave us the motion, but not the meaning. He showed us that the universe is dynamic, but not what lies beyond, if anything. That question requires us to think even more carefully about what we mean by space, by expansion, by the very fabric of reality. Because the answer when it comes won't be what you expect. It never is. Imagine trying to describe the birth of everything using words designed for everyday things. A beginning that wasn't in a place because place didn't exist yet. An explosion that didn't happen in space because space itself was being born. A moment before, which there was no before because time hadn't started ticking. This is the challenge we face when we talk about the Big Bang, and it's why almost everyone gets it wrong at first. The name itself is misleading. Big Bang sounds like a bomb going off matter flinging outward into empty space debris scattering from some central point of detonation. But that's not what happened. There was no center. There was no empty space waiting to be filled. The Big Bang wasn't an explosion in the universe. It was an explosion of the universe and expansion of space itself, from a state so dense, so hot, so incomprehensibly small that our everyday words simply fail. Close your eyes for a moment and picture the entire observable universe, all 93 billion light years of it, compressed down to the size of a grapefruit. Now smaller, an atom, a proton. Smaller still, beyond anything you can visualize, beyond anything physics can currently describe. That's where it began. Not in darkness because darkness is something. Not in silence because silence requires space for sound to fail to fill. Just a singularity, a point of infinite density where the rules we use to make sense of reality break down completely. And then for reasons we still don't fully understand, it started expanding. Not spreading into pre-existing space, but creating space as it went, stretching the fabric of reality outward in every direction at once. There was no outside. There was no edge. Every point in that newborn universe was both the center and the periphery, the source and the destination. If you could somehow have stood anywhere in that first instant, you would have seen the expansion happening all around you as if you were at the heart of creation itself. The common mistake, the one that trips up almost everyone, is thinking of the Big Bang as an event that happened somewhere. People ask, where did the Big Bang happen? And the answer is everywhere. It didn't occur at a location in space. It was the beginning of space. Before the Big Bang assuming, before it even has meaning, there was no stage for events to unfold on. Space and time emerged together, woven into a single fabric that has been stretching ever since. Think of it like this. Imagine the surface of a balloon with no inside, no outside, just the surface itself. Now imagine that surface representing all of space, not floating in some larger void, but existing on its own, complete and self-contained. As the balloon inflates, every point on the surface moves away from every other point. There's no central spot from which the expansion originates. An ant standing anywhere on that surface would see all other ants moving away the distant ones faster than the nearby ones, and yet none of them are moving through the surface. The surface itself is growing. Our universe works the same way, just in 3 dimensions instead of 2. Galaxies aren't flying through space. Space is carrying them along like leaves floating on an expanding river. The river isn't flowing into an ocean. The river is all there is, and it's getting wider, deeper, longer, creating more river as it goes. In the first fraction of a second after the Big Bang, the universe underwent a period called inflation, a moment of exponential expansion so rapid that it dwarfs even the dramatic growth we observe today. In less than a trillionth of a second, space expanded by a factor of at least 10 to the 26th power, smoothing out irregularities, stretching quantum fluctuations to cosmic scales, setting the stage for everything that would follow. Inflation is still a theoretical proposal supported by indirect evidence, but not yet proven beyond doubt. But it solves several puzzles about why the universe looks the way it does, why it's so uniform on large scales, why distant regions that never had time to interact somehow share the same temperature, the same properties. After inflation, The universe was still unimaginably hot and dense, a seething soup of energy and fundamental particles. Quarks and gluons swirled in a plasma so energetic that atoms couldn't form. Photons, particles of light, were constantly absorbed and re-emitted, trapped in an opaque fog of matter and radiation. The universe was bright, searingly bright, but you couldn't have seen anything because light couldn't travel freely. It was scattered, absorbed, redirected over and over, unable to escape the dense tangle of particles. As space expanded, it cooled. This is crucial to understand. The expansion doesn't just create more space. It also dilutes energy, spreads it thinner, lowers the temperature. Think of a gas expanding in a container. As the volume increases, the pressure drops, and the gas cools. The universe works the same way, just on an incomprehensibly larger scale. Every doubling of size halves the temperature, roughly speaking, and as the cosmos grew, it cooled from trillions of degrees to billions to millions, eventually reaching temperatures where particles could slow down, stick together, form the first stable structures. About 3 minutes after the Big Bang, the universe had cooled enough for protons and neutrons to bind together, forming the nuclei of the lightest elements: hydrogen, helium, a trace of lithium. This process, called Big Bang nucleosynthesis, lasted only a few minutes, but determined the elemental composition of the cosmos for billions of years to come. Roughly 75% hydrogen, 25% helium, and tiny amounts of everything else. That ratio is still visible today in the oldest stars in the gas clouds between galaxies, a fossil record written in the proportions of atoms. But the universe was still opaque. Light still couldn't travel freely. It took another 380,000 years of expansion and cooling before the temperature dropped low enough for electrons to combine with nuclei, forming the first neutral atoms. This moment, called recombination, was a turning point. Suddenly, photons could move without constantly scattering off charged particles. Light was set free and the universe became transparent for the first time. Those photons are still out there traveling through space, stretched and cooled by 13.8 billion years of expansion. We call them the cosmic microwave background, or CMB, a faint glow of radiation that fills the entire sky. The oldest light in the universe, a snapshot of what the cosmos looked like when it was just a baby. When you tune an old analog television to a channel with no signal, about 1% of the static you see is leftover radiation from the Big Bang, ancient photons that have been journeying through space since before the first stars ignited. The CMB is one of the strongest pieces of evidence we have for the Big Bang. It's remarkably uniform, the same temperature in every direction, to within a few parts in 100,000, which tells us the early universe was incredibly smooth, almost perfectly homogeneous. But there are tiny fluctuations, small variations in temperature that correspond to regions of slightly higher or lower density. Those fluctuations imprinted in the fabric of space when the universe was just 380,000 years old were the seeds of everything that came later. Gravity amplified them, pulling matter into the denser regions, forming the first stars, the first galaxies, the vast cosmic web of structure we see today. Another common misconception is that the Big Bang was the creation of matter and energy from nothing. It wasn't, at least not in the way most people imagine. The Big Bang describes the expansion of the universe from an extremely hot, dense state. Where that initial state came from, whether it emerged from quantum fluctuations, whether it was part of a larger multiverse, whether it's even meaningful to ask what came before, those are questions that push against the limits of current physics. We can trace the universe back to fractions of a second after the Big Bang, but the moment of the singularity itself, time zero, remains a mystery. A place where our equations break down and we're left with more questions than answers. Some people hear about the Big Bang and imagine it happened a long time ago in a distant place, and we're just observers watching the aftermath. But we're not outside the event looking in. We're inside it, part of it still living in the afterglow of that first expansion. The Big Bang didn't happen somewhere else. It happened here, It happened everywhere. The space you're occupying right now is space that emerged from that initial expansion, stretched and cooled over billions of years. You are quite literally sitting inside the Big Bang, surrounded by its remnants, breathing atoms forged in its fires. And it's still happening. The expansion hasn't stopped. Space is still stretching, galaxies are still receding, the universe is still growing. And in a very real sense, the Big Bang is an ongoing process, not a moment frozen in the past, but a continuous unfolding that we're witnessing in real time. Here's something to sit with quietly. If the Big Bang didn't happen at a location, if it wasn't an explosion into pre-existing space, then what does it mean to say it had a beginning? Can something begin if there was no time before it started? Physicists wrestle with this question, and the answers depend on interpretations of quantum mechanics, theories of gravity that we haven't fully developed yet, ideas that sound more like philosophy than science. Maybe time itself is an emergent property, something that arises from deeper timeless laws. Maybe the universe cycles expanding and contracting in an eternal rhythm. Maybe the Big Bang was just one event in a much larger multiverse, a bubble forming in an infinite sea of other bubbles. We don't know, and that's okay. Not knowing doesn't weaken the evidence for the Big Bang. It just reminds us that the universe is under no obligation to make sense at every level, that there are mysteries woven into the fabric of reality that might take centuries to unravel, or might remain forever beyond our grasp. One of the most beautiful aspects of the Big Bang is how it connects the very largest scales to the very smallest. The expansion of the universe stretching across billions of light years is linked to quantum fluctuations that occurred in the first instance, tiny ripples in the fabric of space-time that grew into galaxies and clusters and the vast cosmic web. The physics of the infinitesimally small and the physics of the cosmically large are not separate. They're woven together, cause and effect, across scales so vast and so tiny that we can barely conceive of them, let alone directly observe. And yet, we've pieced the story together. Not from guesses, not from mythology, but from observations, measurements, equations that describe reality with astonishing precision. We've traced the history of the universe from the first microseconds to the present day, mapped its evolution, predicted what we should see, and then looked through telescopes and found those predictions confirmed over and over. Think about what that means. A species that evolved on a small planet orbiting an average star has managed to reconstruct the history of everything, to peer back to a time when the universe was smaller than a bread box, hotter than the core of any star, denser than anything we can create in a laboratory. We've done this not with magic, not with revelation, but with patience, curiosity, and the humble willingness to follow the evidence wherever it leads. But even with all we've learned, the Big Bang leaves us with a paradox. If the universe is expanding, if it had a beginning, if space itself is stretching, then what, if anything, is it expanding into? We've danced around this question, hinted at the answer, but now it's time to face it directly, because the answer, strange as it sounds, is that the question itself might be the problem, and that realization, when it finally settles in, changes everything. There's a question that haunts every conversation about the expanding universe, a question so persistent, so intuitive that even physicists find themselves returning to it late at night when sleep won't come. If the universe is expanding, what is it expanding into? What lies beyond the boundary? What occupies the space that the universe is growing to fill? The question feels unavoidable, essential, like asking where a river flows or what holds up the sky. But the answer, when it finally arrives, doesn't comfort. It challenges everything we think we know about space, about containment, about the very meaning of outside. The answer is this: the universe isn't expanding into anything. There is no outside. Not because we haven't found it yet, not because it's too far away to measure, but because the concept itself has no meaning. Outside is a word that only makes sense when there's an inside a boundary, a division between here and there. But the universe doesn't have a boundary. It doesn't need one. It is all there is, and asking what lies beyond it is like asking what's north of the North Pole. The question assumes a direction that doesn't exist. Let that sink in for a moment. Not that we don't know what's outside the universe, but that outside the universe is a phrase without referent a grammatically correct sentence describing nothing at all. It's not that the answer is mysterious. It's that the question breaks down revealing assumptions we didn't know we were making about the nature of space itself. To understand why we need to think more carefully about what space actually is. Most of us imagine space as a kind of container, an empty box in which matter and energy move around a stage on which the cosmic drama unfolds. This intuition goes back millennia. Even Newton, who revolutionized physics, thought of space as absolute a fixed background that existed independently of anything within it. If you removed all the matter, all the energy, all the light from the universe, space would still be there empty and waiting, stretching infinitely in all directions. But Einstein's general relativity overturned that picture completely. In Einstein's framework, space isn't a container, it's part of the contents. Space and time are woven together into a single entity space-time, and that fabric is dynamic, capable of bending, stretching, rippling in response to mass and energy. Matter tells space-time how to curve. Space-time tells matter how to move. They're not separate. They're two aspects of the same underlying reality. And here's the crucial part. Space-time is the universe. It's not in the universe. It is the universe. When we say the universe is expanding, we mean space-time itself is stretching, creating more distance between galaxies. Not because they're traveling through space, but because the space between them is growing. There's no pre-existing void for space-time to expand into, because space-time is all there is. Beyond it, nothing. Not empty space, not darkness, not a boundary waiting to be crossed. Just nothing in the deepest, most literal sense of the word. This is where analogies start to help, even though they can never capture the full reality. Imagine living on the surface of a sphere like an ant crawling on a basketball. The ant can move in any direction, forward, backward, left, right, but it never reaches an edge. If it keeps walking, it eventually returns to where it started, having circled the globe. The surface is finite, measurable, but it has no boundary. There's no point where the surface ends and something else begins. Now ask the ant what's outside the surface. The question doesn't make sense from the ant's perspective. The ant only experiences the two-dimensional surface. It can't perceive the three-dimensional space in which the sphere exists. To the ant, the surface is all there is. There's no outside, not because the ant can't reach it, but because outside requires a dimension the ant doesn't have access to. Our universe might work the same way, just in higher dimensions. We live in 3 spatial dimensions plus time, and those dimensions curve back on themselves in ways we can't directly visualize. If the universe is closed like the surface of a sphere, then you could theoretically travel in one direction forever, and eventually return to your starting point, having circumnavigated the cosmos. The universe would be finite in volume, but unbounded, with no edge, no wall, no place where space stops. Or the universe might be flat, extending infinitely in all directions, a limitless expanse that never curves back on itself. In this case, space doesn't have an edge either, but for a different reason. It just goes on forever, an infinite 3-dimensional sheet with no boundary, because there's always more. Asking what's beyond an infinite universe is like asking what number comes after infinity. The question assumes a limit where none exists. Either way, closed or infinite, there's no outside. The universe is complete in itself, self-contained, requiring nothing beyond its own boundaries or lack thereof to exist. But this answer feels deeply unsatisfying, doesn't it? Our brains evolved to navigate 3-dimensional space on a small planet. We're hardwired to think in terms of containers and contents inside and outside, here and there. Every object we encounter in daily life exists within something larger. A book sits on a shelf. The shelf stands in a room. The room is part of a building. The building occupies a plot of land. The land curves around a planet. The planet orbits a star. The star belongs to a galaxy. And surely the galaxy must exist within something, some larger structure, some ultimate container that holds everything. But the universe refuses to play by those rules. It doesn't sit inside anything. It doesn't occupy a location. It simply is, and asking what contains it reveals the limits of our intuition, the places where our everyday experience fails to prepare us for the strangeness of reality. One way to think about this is to consider what we mean by expansion. When we say a balloon is expanding, we picture the rubber stretching the surface area, growing the balloon occupying more space within the room. The room is the background, the pre-existing space into which the balloon expands. But the universe has no room. It has no background. Space itself is what's expanding, and there's no external reference frame to measure that expansion against. Imagine two galaxies separated by 1 billion light years. Over time, that distance increases to 2 billion light years. Where did the extra billion light years come from? Not from the galaxies moving through space. They're barely moving at all relative to their local surroundings. The space between them grew, new distance emerged, and it didn't come from anywhere, because space doesn't have a source. It's not made of anything that can be drawn from a reservoir. It just increases intrinsically as a property of the space-time fabric itself. This leads to another common misconception, one that even scientifically literate people sometimes struggle with. If the universe is expanding, why aren't we expanding too? Why aren't galaxies, stars, planets, atoms, all growing larger along with space? The answer lies in the strength of the forces holding things together. Gravity binds the solar system. Electromagnetism holds atoms together. The strong nuclear force keeps atomic nuclei from flying apart. These forces are vastly stronger on local scales than the expansion of space. The expansion only dominates on the largest scales where gravitational attraction is weak and matter is spread thin. Think of it like this. If you draw 2 dots on a rubber band and then stretch the rubber, the dots move apart. But if you glue a coin to the rubber band, the coin doesn't stretch. Its internal structure is too rigid. The rubber around it stretches, but the coin remains intact. Galaxies are like coins glued to the fabric of space. Space stretches around them, but they don't stretch with it because gravity holds them together more tightly than the expansion can pull them apart. On scales smaller than galaxy clusters, roughly a few million light years, expansion is effectively negligible. The Milky Way isn't getting bigger. The distance between Earth and the Sun isn't increasing. You're not slowly drifting away from the walls of your room. The expansion of space is real, but it's swamped by stronger local forces. It's only when you zoom out to the largest scales, where galaxies are separated by hundreds of millions or billions of light years, that the expansion becomes noticeable, undeniable, the dominant feature shaping the cosmos. Here's a question worth pondering. If the universe has no edge, no boundary, no outside, does that make it more mysterious or less? Does the absence of a container feel liberating, like infinite freedom? Or does it feel claustrophobic, like being trapped in a place you can never escape? Not because there are walls, but because there's nowhere else to go. Some cosmologists have proposed that our universe might be part of a multiverse, a vast ensemble of separate universes, each with its own laws of physics, its own constants, its own history. In this picture, our universe would be just one bubble in an infinite foam of bubbles, each one expanding, each one isolated from the others, unreachable and undetectable, except through indirect theoretical reasoning. If this is true, then, in a sense, there is something outside our universe, namely other universes. But they're not outside in the spatial sense. They're not occupying some larger space that contains both them and us. They're separate spacetimes, disconnected regions of reality that don't share a common spatial framework. It's a mind-bending idea, and it raises as many questions as it answers. If there's a multiverse, what contains it? What's outside the multiverse? And if the answer is nothing, then we're back where we started, just at a higher level of abstraction. The question of outside seems to regress infinitely, always demanding one more layer, one more container, one more boundary to cross. Maybe that's the point. Maybe the universe is teaching us that our need for containment for edges for a final boundary beyond which nothing lies is a quirk of our psychology, not a feature of reality. Maybe existence doesn't need permission to exist. It doesn't need a stage to perform on a void to fill a larger structure to justify its presence. It just is self-contained and complete, and that completeness is so alien to our experience that we struggle to accept it even when the mathematics and observations both point in the same direction. Einstein once said that the most incomprehensible thing about the universe is that it's comprehensible. But maybe the second most incomprehensible thing is that it doesn't need an outside. It doesn't need a reason to exist beyond itself. It's enough just as it is expanding into nothing, because nothing is all there is to expand into. And yet the expansion continues, not just slowly, not just steadily, but accelerating, driven by something we barely understand, a force that seems to be tearing the fabric of space-time apart faster and faster with each passing moment. If the universe has no outside, no boundary, no limit, then what's driving this acceleration? What's pushing galaxies apart with increasing speed? The answer, when we finally discovered it, came as a shock even to those who were looking for it. Because the universe, it turns out, is not just expanding. It's being pulled apart by something invisible, something that fills every corner of space, something that makes up most of the cosmos, and yet remains almost completely unknown. And understanding that force means confronting the unsettling reality that we don't know what most of the universe is made of. In 1998, two teams of astronomers set out to measure how much the expansion of the universe was slowing down. Not if it was slowing, but how much. Everyone assumed gravity would be gradually pulling the brakes on the expansion, the combined mass of all the galaxies tugging on each other, decelerating the cosmic growth that began with the Big Bang. It was just a matter of measuring the rate. Except when the data came in, when the numbers were checked and rechecked and checked again, the teams found something that shouldn't have been possible. The universe wasn't slowing down at all. It was speeding up. The expansion was accelerating galaxies racing away from each other, faster and faster, as if some invisible hand was pulling them apart, overcoming gravity, defying every expectation. It was one of the most shocking discoveries in the history of cosmology, a result so unexpected that the scientists themselves initially thought they'd made a mistake. But the mistake was in the assumption, not the measurement. The universe, it turned out, was full of something we'd never detected, something that pushed instead of pulled, something that filled every cubic centimeter of space and drove the cosmos apart with relentless, unstoppable force. They called it dark energy, and to this day, we have no idea what it is. The discovery began with supernovae, specifically a type called Type Ia exploding stars, that flare up with such consistent brightness that astronomers can use them as cosmic yardsticks. Because Type Ia supernovae always reach roughly the same peak luminosity, you can calculate their distance by measuring how bright they appear from Earth. Dim ones are far away. Bright ones are nearby. It's a technique called standard candles, and it had been used for decades to map the distances to galaxies across the observable universe. The two competing teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rice, were hunting for distant supernovae, measuring their brightness and redshift, plotting the relationship between distance and velocity. The goal was to determine the deceleration parameter, the rate at which gravity was slowing the expansion. A high deceleration would suggest a dense universe that might eventually collapse back on itself. A low one would mean the universe would expand forever, gradually cooling into darkness. But what they found was neither. The distant supernovae were dimmer than expected, which meant they were farther away than they should have been if the expansion were slowing down. It was as if the universe had grown more than predicted, stretched farther than gravity alone would allow. The only explanation was that something was pushing outward, counteracting gravity, accelerating the expansion. At first, both teams suspected errors. Dust between the galaxies could dim the light, making distant supernovae appear farther away. Variations in the supernova themselves could skew the results. Instrumentation glitches, calibration, mistakes, statistical flukes, any of these seemed more plausible than a universe accelerating into the void. But as more data came in, as more supernovae were measured, the pattern held. The acceleration was real. In 2011, Perlmutter, Schmidt, and Reyes shared the Nobel Prize in Physics for the discovery of validation of work that had upended our understanding of the cosmos. But the prize didn't come with an explanation. We know the universe is accelerating. We've measured it, mapped it, confirmed it through multiple independent methods. What we don't know is why. Dark energy is the name we give to whatever is causing the acceleration, but it's more of a placeholder than an answer. We know it exists because we see its effects, the same way we know wind exists because we see trees bending. But what dark energy actually is, where it comes from, how it works, those remain some of the deepest mysteries in all of physics. The simplest explanation, and the one that currently fits the data best, is that dark energy is a property of space itself, a kind of intrinsic energy woven into the fabric of the vacuum. This idea goes back to Einstein's cosmological constant, the term he added to his equations to keep the universe static, the term he later called his greatest blunder. Turns out it might not have been a blunder after all, just a solution in search of the right problem. In quantum field theory, even empty space isn't truly empty. It's seething with virtual particles, pairs of matter and antimatter that pop into existence for a fraction of a second before annihilating each other, a constant quantum fizz that fills the vacuum. These fluctuations carry energy, and if that energy doesn't change as the universe expands, if it remains constant per unit volume, then as space grows, the total amount of vacuum energy grows with it. More space means more energy, and that energy exerts a kind of negative pressure, a repulsive force that pushes space apart. It's a beautiful idea, elegant and mathematically consistent. But there's a problem. When physicists calculate how much vacuum energy should exist based on quantum mechanics, they get a number that's catastrophically wrong, not off by a little. Off by 120 orders of magnitude, the largest mismatch between theory and observation in the history of science. If the vacuum energy predicted by quantum field theory were real, the universe would have torn itself apart in the first fraction of a second. Clearly, something is canceling out most of that energy, leaving only a tiny residue, but we have no idea what or why. That tiny residue, though, is enough to drive the acceleration we observe. Measurements from the cosmic microwave background, the distribution of galaxies and distant supernovas, all point to the same conclusion: dark energy makes up about 68% of the total energy content of the universe, not 2%. Not 20%. More than 2/3 of everything that exists is this mysterious, invisible force that we can't see, can't touch, can't directly detect, only infer from its effects on the motion of galaxies. And here's the eerie part. Dark energy seems to be perfectly uniform, spread evenly throughout space, unchanging over time, at least as far as we can measure. It doesn't clump like matter. It doesn't dilute as space expands. Its density remains constant, which means as the universe grows, the total amount of dark energy increases, pushing the expansion faster and faster, in a runaway process that has no obvious end. Another possibility is that dark energy isn't a property of space itself, but a new kind of field similar to the Higgs field or the electromagnetic field. Something that permeates the universe and exerts pressure. This hypothetical field is sometimes called quintessence, named after the fifth element in ancient philosophy, the substance that filled the heavens beyond the earthly realm of earth water, air, and fire. Unlike the cosmological constant, quintessence would be dynamic, capable of changing over time, its strength and effects varying as the universe evolves. If quintessence exists, it could explain why dark energy seems to dominate now, but not in the early universe, when the cosmos was young and dense matter and radiation controlled the dynamics, gravity slowing the expansion. But as space grew and matter spread, thin quintessence gradually took over, tipping the balance from deceleration to acceleration. The transition would have occurred relatively recently in cosmic terms, perhaps 5 or 6 billion years ago, right around the time the solar system was forming. But quintessence raises its own questions. What is this field? Where does it come from? Why does it have the properties it does? And if it can change, how will it behave in the future? These are open questions, and the answers could reshape our understanding of physics at its most fundamental level. A third possibility, more radical, is that dark energy doesn't exist at all. Maybe the problem isn't that we're missing something in the universe, but that we're using the wrong theory of gravity. Einstein's general relativity has passed every test we've thrown at it on scales, from the solar system to galaxies, but perhaps it breaks down on the largest scales where the distances are so vast and the densities so low that new effects emerge. Modified gravity theories propose tweaks to Einstein's equations that could produce the observed acceleration without invoking dark energy, explaining the data through a deeper understanding of how space-time behaves. These theories are intriguing, but they come with their own challenges. They have to reproduce all the successes of general relativity, while also explaining the acceleration, and so far, none have managed to do both convincingly. General relativity remains our best description of gravity, and dark energy, mysterious as it is, remains the leading explanation for the accelerating expansion. One of the most unsettling aspects of dark energy is what it implies about the future. If the acceleration continues, and current evidence suggests it will then, over billions of years, the universe will become an increasingly lonely place. Galaxies beyond our local group already receding from us will move farther and farther away. Their light redshifted into invisibility, their images fading from the sky. Eventually, only the Milky Way and its nearest neighbors will remain visible. A small island of light surrounded by an ever-expanding darkness. Imagine astronomers in the far future, trillions of years from now, looking up at the night sky. They'll see a handful of stars in their own galaxy and nothing else. No distant galaxies. No cosmic microwave backgrounds stretch beyond detection. No evidence that the universe was ever larger, that it had a beginning, that other galaxies even existed. They will have no way to discover the Big Bang, no way to measure the expansion, no way to infer the existence of dark energy. The universe they observe will seem static, eternal, bounded by the edge of their galaxy, a small, isolated cosmos, adrift in an infinite void. In a sense, they'll be back where we were a century ago before Hubble, before we knew the universe was expanding. Except we have evidence and they won't, because dark energy will have erased it, carrying the proof of cosmic history beyond the horizon of what can ever be seen. It's a sobering reminder that our window of understanding is temporary, contingent on the accident of living in an era when the universe is still young enough, still dense enough that the traces of its past remain visible. Here's a question that might linger. If dark energy makes up more than 2/3 of the universe, and we have no idea what it is, can we really claim to understand the cosmos at all? Or are we just scratching the surface, mapping the visible 5%, while the rest remains hidden, inscrutable, waiting for a breakthrough that might never come? The discovery of dark energy forced physicists to confront a humbling truth: we don't know what most of the universe is made of. Not just dark energy, but dark matter too. The invisible mass that holds galaxies together accounts for another 27%. Combined dark matter and dark energy make up 95% of the total content of the cosmos. Everything we can see, every star, every planet, every atom in your body is just a tiny fraction of what exists, a thin foam floating on an ocean of mystery. And yet, we keep probing, keep measuring, keep building better telescopes and more sensitive detectors, hoping to catch a glimpse of the invisible to understand the forces shaping our fate. Dark energy is out there filling the void, driving the expansion, pulling the universe apart, thread by thread. And we're watching it happen, in real time, even if we can't explain why. The acceleration also raises philosophical questions about the nature of existence. If dark energy is real, if the vacuum itself carries energy, then empty space is not nothing. It's something active and dynamic, capable of exerting force shaping the destiny of the cosmos. The old idea of a void, a passive background on which events unfold, dissolves completely. Space becomes an agent, a participant, a field of potential that influences everything within it. And if space can do that, if it can push galaxies apart, drive the expansion, dominate the energy budget of the universe, then what else might it be capable of? Are there other properties of the vacuum we haven't discovered yet? Other forces, other fields, other dimensions hiding in the structure of reality, waiting to be revealed? We don't know. But we're learning to ask better questions, and sometimes that's the first step toward understanding. Dark energy might remain a mystery for decades or centuries, or it might be solved in the next breakthrough, the next observation that cracks the puzzle wide open. Either way, the fact that we can even ask these questions, that we can measure the acceleration map, its effects trace its influence across billions of light years, that's extraordinary. Because the universe isn't obligated to make sense to us. It could have been opaque, unreadable, a chaos beyond comprehension. But it's not. It's governed by laws, patterns, regularities that we can discover, test, refine. Dark energy is a mystery. Yes, but it's a mystery we can study, a puzzle with clues scattered across the sky, waiting for someone clever enough, patient enough to piece them together. And when we finally understand what's driving the expansion, when we crack the code of dark energy, the answer will almost certainly lead to new questions, deeper mysteries, stranger truths. Because that's how the universe works. Every answer opens a door, and beyond that door lies not closure, but more cosmos, more wonder, more reasons to keep looking. But even as we search for answers, the acceleration continues, relentless and unstoppable, pushing the galaxies farther apart, stretching the fabric of space, shaping the future in ways we're only beginning to grasp. And that future, distant though it may be, is already written in the stars, or rather in their absence. There will come a time unimaginably far in the future when the last star flickers out. Not suddenly, not dramatically, but slowly, quietly, like a candle burning down to nothing, in a room where no one is watching. The universe will grow cold, silent, empty. Galaxies will drift so far apart that their light can never reach each other. Matter itself might decay, particles dissolving into radiation, spreading thinner and thinner until even the memory of structure fades into uniformity. This is not speculation. This is what the mathematics predicts, what the observations suggest, what the laws of physics whisper when we trace them forward into the deep future. The universe had a beginning. That much we know. But will it have an ending? And if so, what kind? The answer depends on dark energy, on the expansion, on forces we barely understand, shaping a destiny we can glimpse but not control. 3 scenarios emerge from the equations, 3 possible fates for everything that exists. None of them are comforting, but all of them are beautiful in their own way, reminders that even endings can carry a strange, austere elegance. The first scenario, and currently the most likely based on observations, is called the Big Freeze, though some prefer the term heat death. It's a slow fade, a gradual cooling and expansion that continues forever, carrying galaxies farther and farther apart until the universe becomes a vast, dark, nearly empty expanse where nothing new can happen. To understand why we need to think about entropy, the tendency of systems to move from order to disorder, from concentrated energy to diffuse equilibrium. Right now, the universe is out of equilibrium. Stars burn, planets orbit, galaxies collide, life evolves. All of this requires energy gradients, differences in temperature concentrations of matter that can do work, create structure, drive change. But those gradients won't last forever. Stars consume their fuel and die. Black holes evaporate through Hawking radiation. Even protons, if current theories are correct, might eventually decay, breaking down into lighter particles over time scales of 10 to the 36th power years or longer. As the universe expands, energy spreads thinner. The cosmic microwave background, already cooled to just 2.7 degrees above absolute zero, will continue to redshift, its temperature dropping asymptotically towards zero. Dark energy will keep pushing galaxies apart, and eventually the only objects still bound together by gravity will be within our local group, a small cluster of galaxies that includes the Milky Way, Andromeda, and a handful of smaller companions. Everything else will have receded beyond the cosmic horizon, their light stretched so thin by expansion that it never reaches us, their existence erased from our observable universe. Within our local group, stars will continue to form for a while, condensing from gas clouds, igniting, burning through their fuel and dying. But the supply of gas is finite. Once it's exhausted, no new stars will be born. The existing ones will age, the massive ones exploding as supernovae, the smaller ones fading into white dwarfs, slowly radiating away their remaining heat over trillions of years. Eventually, perhaps 100 trillion years from now, the last star will go dark and the universe will enter what's called the degenerate era, a time when the only light comes from the faint glow of cooling embers, white dwarfs, and brown dwarfs too small to sustain fusion. But even that faint light won't last. White dwarfs will cool into black dwarfs, objects so cold they emit no detectable radiation. Brown dwarfs will fade completely. The universe will be dark, illuminated only by the occasional flash of two dead stars colliding, a brief flicker in an otherwise endless night. This era could last for 10 to the 40th power years or more, an expanse of time so vast that the entire history of the universe so far, all 13.8 billion years of it, is less than a heartbeat in comparison. And then comes the black hole era. During this period, black holes will dominate what little structure remains. They'll grow by merging with each other, by accreting the sparse matter drifting through space. But they'll also shrink slowly, evaporating through Hawking radiation, a quantum process that allows black holes to lose mass over time. Small black holes evaporate quickly. Massive ones, like the supermassive black holes at the centers of galaxies, will take unimaginably long, perhaps 10 to the 100th power years, a Google years, before they finally disappear in a last faint burst of particles. Once the black holes are gone, the universe enters its final state, the dark era. Space will be filled with nothing but a thin soup of elementary particles, photons, electrons, positrons, maybe neutrinos, all spread so far apart that they almost never interact. The temperature will be a fraction of a degree above absolute zero. Entropy will have reached its maximum. No energy gradients will remain, no work can be done, no structures can form. The universe will have achieved perfect equilibrium, a state of maximal disorder from which nothing new can emerge. This is heat death, not an explosion, not a collapse. Just silence stretching on forever, a cosmos that has exhausted all its possibilities and settled into a final, unchanging stillness. It's a fate that feels almost unbearably sad, the idea that all of this, all the stars and galaxies, all the life and consciousness, all the beauty and struggle will one day dissolve into cold, empty uniformity. But there's also something peaceful about it, a kind of rest, a conclusion to the story that began with the Big Bang. Of course, this assumes dark energy remains constant, that the acceleration continues at its current rate without change. But what if it doesn't? What if dark energy grows stronger over time, increasing its repulsive force, pushing galaxies apart faster and faster until the expansion becomes catastrophic? This leads to the second scenario, the Big Rip, and it's far more violent than the Big Freeze. In the Big Rip, dark energy doesn't just push galaxies apart, it tears them apart. As the repulsive force increases, it eventually overcomes not just the large-scale structure of the universe, but the smaller-scale structures too. First, galaxy clusters unbind their member galaxies, drifting away from each other. Then, individual galaxies disintegrate, stars scattered into the void. Then, solar systems break apart, planets flung into interstellar space. Then, planets themselves are shredded, their atoms pulled apart by the relentless expansion of space. Eventually, even atoms can't hold together. The electromagnetic force binding electrons to nuclei, the strong nuclear force holding protons and neutrons in the nucleus, all of these become weaker than the tearing force of space itself. Matter dissolves into its constituent particles, and those particles scatter into isolation alone in a universe expanding so fast that nothing can remain connected. The timescale for the Big Rip depends on how quickly dark energy grows. Some models suggest it could happen in as little as 22 billion years. Others push it further into the future. But the outcome is the same: total disintegration, a cosmos ripped to shreds by its own expansion. It's a more dramatic ending than the Big Freeze apocalyptic, where the other was elegiac, but it's also less likely based on current observations. The data so far suggests dark energy is consistent with a cosmological constant, unchanging over time, which favors the Big Freeze over the Big Rip. But uncertainty remains. We don't know what dark energy is, and if we don't know what it is, we can't be sure how it will behave in the future. The Big Rip is still on the table, a possibility we can't rule out until we understand the nature of the force driving the acceleration. The third scenario. The Big Crunch is the one scientists once thought most likely back before the discovery of dark energy. In this version, the expansion eventually slows, stops, and reverses. Gravity wins. Galaxies begin falling back toward each other, slowly at first, then faster until the entire universe collapses into a singular point, a mirror image of the Big Bang. Space contracts, temperatures rise, matter compresses, and everything that ever existed converges into a final searing moment of infinite density. It's a poetic ending, a cosmos that breathes in and out, expanding from a singularity, evolving, cooling, then contracting back into the furnace from which it came. Some cosmologists speculated that the Big Crunch might even trigger a new Big Bang, a cyclic universe that expands, collapses, and reemerges over and over, endlessly repeating, never truly ending. It was a comforting idea, a way to avoid the finality of heat death, the violence of the Big Rip, the unsettling notion that everything might simply fade away. But the Big Crunch requires the universe to be dense enough for gravity to overcome the expansion, and observations show that it's not. The combined mass of all the matter, both visible and dark, isn't enough to halt the acceleration. Dark energy dominates, and as long as it does, the universe will keep expanding. The Big Crunch, elegant as it might be, seems ruled out by the data. The cosmos is not going to collapse. It's going to drift apart slowly or violently, but inexorably into a future where isolation is the rule and connection the rare exception. Here's a question worth sitting with. Does it matter how the universe ends? Does the knowledge that stars will one day go dark, that galaxies will scatter, that even atoms might dissolve, does that change the meaning of what we do now? Or is the meaning independent of the ending, rooted in the present, in the choices we make, the connections we form, the beauty we create and appreciate while we can? There's a common misconception that the eventual heat death of the universe makes everything meaningless, that if nothing lasts forever, then nothing matters at all. But that confuses duration with value. A sunset doesn't lose its beauty because it fades. A piece of music doesn't lose its power because it ends. Meaning isn't something the universe grants us. It's something we create here and now, in the brief window of time we have to experience, to feel, to understand. And we do understand more than any species that came before, more than our ancestors could have imagined. We've traced the history of the cosmos, from the first microseconds to the present, mapped its structure across billions of light years, predicted its future over time scales that dwarf the age of stars. That understanding is itself a kind of triumph, a way of transcending our smallness, our brevity, our cosmic insignificance. Because, yes, we are small, fragile, temporary. A thin film of life clinging to a rocky planet, orbiting an average star in one galaxy among hundreds of billions, all of it destined to fade. But we are also the part of the universe that knows it exists, that looks up at the stars and asks why, that builds telescopes and writes equations and pieces together the story of creation from scattered photons and redshifted light. That's not nothing. That's extraordinary. The far future might be dark and cold and empty, but it's also unimaginably distant. Trillions of years separate us from the last stars fading. In the meantime, there's so much still to happen. Galaxies will collide, stars will be born, planets will form, and who knows what life might emerge, what civilizations might rise, what wonders might unfold in the eons ahead. The universe is still young, still full of potential, still writing its story. And even in the deep future, in the dark era, when entropy has won and nothing new can happen, there's a strange beauty in the thought of a cosmos, at rest, no longer struggling, no longer burning, just existing in perfect silent equilibrium. It's not the ending we might wish for, but it's the ending the laws of physics predict. And there's something humbling about accepting that, about recognizing that the universe doesn't owe us eternity. One last thought before we drift toward the final reflection. The three scenarios: big, freeze, big, rip, big, crunch. They're all extrapolations based on what we know now. But history teaches us that the universe loves to surprise us. Every time we think we've figured it out, every time we draw a map and say this is how it works, new observations emerge, new data arrives, and the map has to be redrawn. Dark energy was a surprise. The accelerating expansion was a surprise. Who's to say there won't be more surprises ahead? New forces, new fields, new physics that change the trajectory of everything. Maybe the universe will end in heat death. Maybe it will be torn apart in a big rip. Maybe something we haven't even conceived of yet will reshape its destiny. The only certainty is that we don't have all the answers, and maybe we never will. But the search for those answers, the willingness to keep asking, keep observing, keep following the evidence wherever it leads, that's what makes us human. That's what makes this brief flicker of consciousness worth protecting, worth celebrating, worth holding on to for as long as we can. Because in the end, whether the universe fades or tears or collapses, whether it lasts a trillion years or a Google, the fact that we were here, that we saw it, that we wondered and understood even a fraction of its vastness, that might be the most meaningful thing of all. Not because it changes the ending, but because it changes us, makes us part of the story, participants in the cosmic drama unfolding across space and time. And with that, we've traced the arc from beginning to end, from the first expansion to the final silence. But before we close our eyes and let sleep carry us away, there's one more thing to sit with, one more truth to acknowledge, quiet and strange, and ultimately freeing. We've traveled far tonight, from ancient philosophers throwing imaginary spears at the edge of the cosmos, to Einstein wrestling with equations that refuse to stay still, from Hubble discovering galaxies fleeing into darkness, to the shocking revelation that the universe is not just expanding, but accelerating, driven by a force we cannot see, cannot touch, cannot explain. We've stood at the birth of everything and glimpsed the far future, when the last stars fade into silence. And through it all, one question has followed us like a shadow, persistent and unanswerable. If the universe is expanding, what is it expanding into? By now you know the answer, or at least the best answer we have. The universe isn't expanding into anything. There is no outside, no container, no pre-existing void waiting to be filled. Space itself is what's expanding, creating more distance, more room, more universe, not by claiming territory from somewhere else, but by simply being more than it was. It's a truth that defies everyday intuition, that challenges the very way our minds are built to understand the world. And yet, the mathematics supports it, the observations confirm it, and the universe, indifferent to our comfort, continues expanding whether we comprehend it or not. But here's the thing, and this is what I want you to carry with you. As you drift towards sleep, not knowing everything doesn't diminish the wonder. It amplifies it. The universe could have been simple, predictable, a clockwork machine we figured out centuries ago and set aside as solved. Instead, it's strange layered full of mysteries that reveal themselves slowly, each answer opening onto deeper questions, each discovery reminding us how much we still have to learn. That's not a failure of science. That's the gift of existence, the invitation to keep looking, keep asking, keep marveling at how much beauty hides in the unknown. Think about the journey we've taken. For thousands of years, humans looked up at the stars and assumed they were fixed points on a celestial sphere, unchanging, eternal, the backdrop against which earthly dramas played out. Then we discovered the stars were suns scattered across vast distances, each one a furnace burning in the void. Then we found that our sun was just one of billions in a galaxy, and that galaxy was just one of billions more, and all of them were moving, drifting apart, carried by the expansion of space itself. Each step in that journey required someone to let go of what felt certain, what seemed obvious, what everyone believed to be true. Aristotle had to be wrong for Copernicus to be right. Newton had to be incomplete for Einstein to succeed. Einstein had to abandon his static universe for Hubble's observations to make sense. And Hubble's steady expansion had to be incomplete for us to discover dark energy, the accelerating force reshaping the fate of everything. At every stage, the universe revealed itself to be stranger, larger, more complex than we imagined. And at every stage we adapted, we learned we adjusted our models to fit the evidence. That process, that willingness to be wrong in service of being more right, is the beating heart of science. It's what separates understanding from belief, knowledge from dogma, progress from stagnation. And it's still happening. Right now, telescopes are peering deeper into space than ever before, measuring the cosmic microwave background, with exquisite precision tracking the motion of galaxies across billions of light years, searching for clues about dark energy, dark matter, the shape of the universe, the nature of time itself. We don't have all the answers yet, but we're getting closer, one observation at a time, one equation at a time, one careful, patient, humble step at a time. So, what is the universe expanding into? Maybe that's the wrong question. Maybe the better question is, what does the expansion tell us about the nature of reality? And the answer is profound. It tells us that space and time are not separate from the universe. They are the universe. It tells us that the cosmos had a beginning, not in a place, but everywhere, not in time, but as time. It tells us that endings are real, that everything is temporary, that even stars and galaxies are just chapters in a story that will one day conclude. But it also tells us that we are part of that story. Not observers standing outside looking in, but participants woven into the fabric of space-time, made of atoms, forged in the cores of dying stars, breathing oxygen created in supernovae, thinking thoughts powered by energy that traces back to the Big Bang itself. We are the universe looking at itself, trying to understand itself, marveling at its own existence. That connection, that continuity between the cosmos and consciousness is one of the most beautiful truths science has ever uncovered. There's a quote from the astronomer Carl Sagan that feels fitting here. He said, "We are made of star stuff, a poetic way of expressing a literal fact. The carbon in your cells, the iron in your blood, the calcium in your bones, all of it was synthesized in the heart of a star that lived billions of years ago, burned through its fuel, and exploded, scattering its enriched ashes into space. Those atoms drifted through the void, condensed into new clouds, collapsed under gravity, formed a new star, our sun, and the rocky debris around it became Earth. And here you are, billions of years later, a walking, thinking collection of stardust trying to understand where you came from and where you're going. That's not just science, that's poetry. That's meaning written in the language of atoms and light a story that connects the smallest particle to the largest galaxy, the briefest human life to the 13.8 billion year history of everything. And you don't need to understand every detail to feel the weight of it, the wonder of it, the sheer improbability and beauty of being here now, alive and aware in a universe that had no obligation to produce awareness at all. Here's a question for you. One last thought to turn over quietly in your mind. If the universe is expanding, if space itself is growing, if the galaxies are drifting farther apart, does that make the cosmos lonelier? Or does it make the moments of connection, the brief windows when matter clusters into stars and planets and life? Does it make those moments more precious, more meaningful because they're so rare, so fleeting, so utterly contingent on forces we barely understand? I think it does. I think the expansion doesn't diminish us, it elevates us. Because in a universe that could have been empty, formless, a void without structure or purpose, we get this galaxy spiraling through the dark stars, burning bright planets swirling with weather, and life minds capable of asking why and figuring out at least part of the answer. That's not nothing. That's a miracle, even if it's a miracle explained by physics. And the fact that we don't know everything, the fact that dark energy remains a mystery, that the ultimate fate of the universe is uncertain, that the question of what lies beyond our cosmic horizon might never be answered. That's okay. That's more than okay. Because the not knowing is what keeps us curious, what drives us to build better telescopes, write better theories, ask better questions. The mystery isn't a wall, it's a horizon, always receding, always inviting us to take one more step, see one more thing, understand one more piece of the puzzle. Maybe the universe doesn't expand into anything because it doesn't need to. Maybe it's complete in itself, self-contained whole, and asking what's outside is just our minds struggling to fit infinity into concepts designed for finite things. Maybe the real lesson here is that the universe is under no obligation to make sense on our terms, and our job isn't to force it into familiar shapes, but to meet it where it is, accept its strangeness, and marvel at the fact that we can understand any of it at all. We've covered so much ground tonight: the ancient debates over infinity and edges, Einstein's cosmological constant, the mistake that turned out to be prescient, Hubble's discovery that the universe is in motion, the Big Bang not an explosion in space, but an explosion of space, the realization that there is no outside because outside doesn't exist, dark energy, the invisible force tearing everything apart, and the far future when the stars go dark and the cosmos settles into its final silence. All of it, every piece fits together into a single narrative, a story of a universe that began small, grew vast, and will one day grow cold. But that story isn't finished. We're still in the middle chapters, still watching the plot unfold, still discovering new twists, new characters, new possibilities. And the best part, we get to be here for it. We get to witness this moment in cosmic history, this brief window, when the universe is young enough to remember its birth, old enough to have produced complexity and just the right age for beings like us to look up, ask questions, and find answers. So, as you feel yourself beginning to drift, as your thoughts soften and blur at the edges, as sleep reaches out to pull you gently into its embrace, remember this: the universe is expanding. Yes, but it's not expanding into anything, because it is everything. Space and time, matter and energy, stars and silence, all of it woven into a single unbroken whole. There is no edge to reach, no boundary to cross, no final wall marking the end of existence. Just the endless patient stretching of space, carrying galaxies into the dark, creating distance where none existed before, and doing so without permission, without explanation, without needing us to understand. And yet, we do understand at least a little. We've looked at the redshift of distant galaxies and calculated the rate of expansion. We've measured the cosmic microwave background and traced the universe back to its first moments. We've discovered dark energy and mapped its effects across billions of light years. We've done all of this with nothing but our minds, our mathematics, our stubborn refusal to accept mystery as an excuse for not trying. That's the human spirit at its best. Curious and relentless, humble and bold, willing to admit ignorance while striving for insight. And the universe, for all its strangeness, for all its refusal to conform to our intuitions, rewards that effort. It reveals itself slowly, patiently, in fragments and glimpses, offering just enough clarity to keep us searching, just enough mystery to keep us humble. It's a partnership in a way between the cosmos and consciousness, between the vast and different machinery of physics and the small, brief sparks of awareness that emerge from it, asking why and how and what comes next. You don't need to solve the universe tonight. You don't need to hold every answer in your mind, understand every equation, grasp every implication. Just rest in the knowledge that we've come so far, learned so much, and that the journey continues with or without us, but richer because we're part of it. The expansion will go on. Space will keep stretching. Galaxies will keep drifting. And somewhere on a small planet orbiting an average star, beings will keep looking up, keep wondering, keep asking the questions that have no final answers but infinite value in the asking. Sleep well, knowing that the universe is vast and strange and beautiful beyond measure. Dream gently knowing that you are made of stars, connected to everything part of a story that began 13.8 billion years ago and will continue long after your brief chapter ends. And when you wake, if you look up at the night sky and feel that old familiar pull, that sense of wonder mixed with vertigo, remember the universe isn't expanding into anything. It's just being more of itself, and that's enough. It's always been enough. Thank you for drifting with me through this quiet exploration of the cosmos. Thank you for your patience, your curiosity, your willingness to sit with strangeness and let it settle into something like understanding. These journeys through science and wonder are only possible because you're here, listening, thinking, feeling the weight of these truths in the quiet of the night. If you found peace in this story, if it helped you see the universe a little differently, I hope you'll stay for the next journey. There are so many more mysteries to explore, so many more questions to ask softly into the dark. Until then, rest well. Dream of galaxies spinning through the void of space, stretching into forever, of stars that burn bright and then fade, leaving only light and memory. Good night,